I figured I'd go over this while it's still fresh, just to kind of provide an intuitive and alternate approach that I think most people teach, because I think this has really worked for me in understanding Taylor MacLaurin series. So we'll go over kind of first this notation, because I think this is kind of key to understanding Taylor MacLaurin series, really. And after we kind of explain the meaning of this notation, then we'll actually solve two problems using this approach to kind of show you how, using kind of the first principle approach here, you can actually naturally arrive at the same conclusion that this states. So if you're like me, I think all of like the series and sequences was like pretty easy up to this point. And I think where this part got difficult for me was like just kind of the notation and all the different ways people were trying to explain it. So I think by kind of sharing this more intuitive approach, this might actually help other people. So that's kind of why I'm here. So I think first thing we need to get at is kind of define what this actually represents. You've probably seen this. Again, I'm assuming you have some familiarity with Taylor series and MacLaurin series and you're trying to understand it better. So I won't like fully go over like, you know, all the assumed prerequisites, like you should know power series, representations of functions power series, all the different tests, convergence and divergence. You should be familiar at least to some degree with all of that. So again, we'll go over this coefficient sequence formula, which is the heart of the Taylor MacLaurin series. So when you're kind of looking at this, it can be a bit overwhelming. And I think that most professors don't either have the time or they're kind of too far away from the learning point to really understand that this is actually like a big part of where I think people get lost. So again, I'm going to go over that for you here. So this part right here, this is just saying that this is a coefficient sequence. And the coefficient sequence is kind of the root of all of this. I think if you don't understand this part, then you're not going to understand why all of this is necessary. So it's really important to understand that the coefficient sequence is, again, we know a sequence is, or rather you should know, or at least be, like when I say this, it should like jog something in your memory. A sequence is just some list of terms, right? And you can define the difference in the terms by some function, usually, and that's kind of how the sequence is expressed, right? So the coefficient sequence is just showing you basically how the coefficients of the series are formed and generated, right? And that's what we get from doing all of this kind of esoteric looking notation here. This is what it's going to produce, right? So the end goal is always just to get coefficients, right? You may be wondering, why exactly is the coefficient important? You know, I thought the whole point of, you know, Taylor series is that we're making a series of polynomials that allow us to approximate. You know, you've probably seen this, I think, is like a pretty popular thing that teachers use because it looks cool, has like a whole bunch of curves and like lines and everything. And that's like supposed to represent that, you know, as you add more and more terms, right, you get a better and better approximation. Because we know that with differentiation and integration, you know, area under curves and instantaneous slope and all of that, we know that that allows us to get approximations, anticipate rate of change, all of that. So speaking about derivatives, that's actually a very, very important part of what makes this work, right? So this notation here, this was unfamiliar to me, so I'll explain it. It just means that you're taking the nth derivative of something, right? It's just shorthand for writing this, because you might say what, I don't know, the 10th derivative. So you don't want to have to write, you know, 10 apostrophes. I didn't even count if that's 10 apostrophes, I don't know. So instead of writing, you know, 10 apostrophes, you can just take the 10th derivative, that notation. And that's all that means. Why we're taking the derivative, again, we'll get into later, but I think it's important just to define pretty clearly what each part of this means, right? This is a coefficient sequence, is all this is saying. And then, again, the coefficient sequence is generated by this whole expression here. This part is just saying that we want the nth derivative of the function. And then this is saying we should evaluate that nth derivative to 0, or by 0, right? So when we take the nth derivative, right, we're going to say it was, I don't know, x. We just set x equal to 0. That's all it's saying. It's as simple as that. And really, it's going to sound like, I don't know if this is the best thing to say, but it's really a lot more simple than it seems, which is kind of crazy when I'm having to explain each part of it piece by piece. But it really is like, once you understand each part of this, everything kind of clicks and makes sense. And you start seeing this less as some weird, like, jumbling of characters, and instead as a tool you can use to analyze functions and expressions, right? So let's talk about this part here. Or rather, let's talk about this part first, because this part is going to require a bit more. And we're going to have to kind of talk about all of this at one point. But this part here, right, this just represents the center, right? Again, if we go back to the graph, you know, we had some crazy function, and we approximate it by using like a tangent line, and then we add a quadratic function, then we add some cubic function, we get better and better approximations of the function as a whole, right? And so we can use that to get a better and better approximation of the function value for some given interval, right? And again, you have to remember that this is always in the context of over some interval, right? We're not trying to evaluate the series, or generally we're not trying to evaluate the series for every single function value. We're just trying to do it for the one that we're interested in, right? And of course, you could do it for every single value, but that's an intensely computational task to perform, especially as the complexity of the function grows. So all this is saying is that, you know, as n increases, as the power of the basis function that we're using increases, obviously we're going to kind of get a little bit further from the center, right? This tangent line is a pretty good approximation of that exact point. But the quadratic line that we get, it's less about here, right? It's less about this point and more about this point right here, to where, you know, it goes off the line again. And the cubic function, similarly, is more about maybe this part and this part, right? So we have, let's do, I don't know, blue for like here, and then let's do like orange for the cubic, and then, I don't know, green for the quartic. I honestly don't remember what a quartic looks like, but we'll just assume that, you know, we can follow the curve a little bit more. And yeah, that's kind of what we're really doing with a Taylor series, right? And you'll notice again that this is covering points kind of further and further away from our original starting point, which was the linear function, or really in this case, you would probably actually assume that it's some just arbitrary point on the function graph, or rather the original function itself. So again, as we're increasing our distance from the center, shifting it by a value of a, and as the power of that basis function increases, or, you know, as we use linear, a quadratic, then a cubic, then a quartic, then that shows, you know, the behavior of the nth order approximation of the function at that point. Essentially, a lot of words just to say that we basically change which function we're using, and the magnitude of that basis function that is shifting with each term in the series, rather, is represented. I think we set our color to this when it needs to be this. And the magnitude is represented by that. So we talked about it a little bit earlier. Again, this is a coefficient sequence. This is meant to generate all of that. But the coefficient, you'll notice, again, if we're trying to generate a coefficient sequence, but we look at a series, right, and it's like 1 plus x squared plus x cubed. Isn't it really more about this? Well, that's what you think, and I think we've been trained to think of polynomials in that sense. But a polynomial is really little more than this, right? So what I mean, let's do a constant, it's a linear, plus a quadratic, plus a cubic, right? We would say this is a cubic polynomial because a polynomial is typically defined by the highest degree. But really, polynomials in general are better thought of as vectors, in my opinion. And not really even in my opinion, it's just the teachings of higher order mathematics tend to treat these more as like vectors and coordinates rather than just some arbitrary functions, right? Because I think especially with algebra, the way it's taught is you kind of tend to focus more on x or some dummy variable because you're used to like solving for it, canceling it, a whole bunch of things. But that kind of makes you forget the actual point of the variable, right? And all the variable is doing is telling you like not how much, but rather that that particular block of the function, right? It's telling you the shape of that function, right? And you can kind of think of a graph like that, right? We know quadratic is like this, you know, linear is like this, you know, cubic is like this, and so on, right? So when you think of this as just kind of telling you the shape, then we know that the coefficient tells you the magnitude or the amount of that shape that you're going to get. And we know that when we add polynomials, right, you're not adding the powers together, right? When we have 2x squared plus 3x squared, you're not getting 2 plus 3 x to the fourth, right? That doesn't make any sense, right? Or you wouldn't do like 2x4 plus 3x4, right? You're not adding the powers, you're adding the coefficients in front of them. Because again, that's telling you how many of that you have. So if you had, I don't know, 2, 3, 4, 5, right? You add these polynomials together, let's again say 2x plus 3x squared plus 4x cubed plus 2 plus 3x plus 4x squared plus 5x cubed. When you add these together, you know, you're taught, you know, let's group like terms. This and this and this and this, right? This is what you're typically taught. I'll just group them together. It'll be like 1 plus 2 plus 2x plus 3x, right? But really, I mean, when you think about it, all you're doing is just a simple vector operation. You're doing 1 plus 2, 3, plus 2 plus 3, 5x, plus 3 plus 4, 7x squared, plus 4 plus 5, 9x cubed, right? That's all you're doing, and you're done. When you set x to some value, then I'll tell you the final value of the equation. But really, a lot of it is just based on the coefficients. So, whole lot of words to then say this, right? We know that when we differentiate a function, we kind of expose some underlying behavior, right? And that underlying behavior is kind of placed with the coefficient, isn't it? Because if we take the derivative of some function, right? We take, let's say we have some function, I think this is a better way to put it. So let's say we have a function, a to the n. The derivative of that function is then n times a n minus 1. If you remember from calculus, this was the form you're taught, but really, you know, in practice, you don't really remember this form because like you see something like this, 6x to the n on a third, you know, it's pretty simple for you at this point. You just do 18x squared, right, by the power rule. But when we think about what a derivative is really doing, and we kind of internalize that, right? So then when we take the derivative of something, again, when we take the derivative of, or rather, let's set f of x equal 5x to the fifth, right? When we take the derivative of it, let's take the first derivative, times 5, 25, x fourth, right? Aren't we every time kind of losing that original coefficient, right? And that, again, original coefficient is very important because it tells us the magnitude of these building blocks, right? But as we, you know, differentiate, we're only getting that current building block's magnitude, right? Take the second derivative, we're going to get 100x to the third derivative equals 300x to the fourth derivative is going to be, oops, that should be 2, and then 600x, and then the fifth derivative is just going to be 600, right? After we've done all that, we're a long way from our original coefficient, right? So how do we account for that? Well, we see here, this is a pretty big hint, right? But let's actually see how it kind of comes into play. And you might kind of already see it, especially if I do this. Although we're not going to multiply by that one. So We just multiply everything by the succeeding power. Oh, that would be 5 factorial. What's 5 factorial equal to? 1 times 2, 2 times 3, 6 times 4 is, 24 times 5 equals 120. So 5 factorial is equal to 120. Well, what if we divide our final coefficient by 5 factorial? This should, let's use 12 as the common factor. Excuse me. That should leave us with 50 over 10, and that simplifies down to 5, which, isn't that our original coefficient? So you see, by using this n factorial to be a kind of scaling ratio, kind of compensation factor, we can kind of recover that original coefficient, and it's not lost, which is very important because we need that to actually craft the coefficient sequence, right? Because we need to see how that coefficient is changing throughout the sequence with the basis function. So now that we've defined every part of it and kind of inspected more about polynomials and gotten a better idea, let's actually solve some stuff. So let's do, I think the easiest one to start with first is e to the x, just because of the way it works with differentiation. And then we'll go to a different problem to see how it works with a different variation of the coefficient, right? So anytime you're faced with a question like this, you just want to start with this. You want to pull up the formula, memorize it, get used to writing a lot, at least when you're first starting. Then obviously you can shorthand it. But this is actually, when you stop looking at this as a formula and more of as an instruction, I think these problems begin to get a lot easier. So when you look at it, you're just looking, you just want each part of this expression, right? This is what you're trying to find. You're trying to put the whole thing together, and then when you have the whole thing together, that's the series. That's what you're looking to make. So what's the first thing we need to do? Well, we can start here. It's on the left. Why not? So we're looking for the nth derivative, and then we're going to value the derivative as 0, right? So let's do, I don't know, let's go up to 3 or 4 terms, right? Let's do the first derivative of e to the x. Well, we should have a pretty good idea of what this is going to result, right? This should be just e to the x every single time, right? Actually, we don't even need to write this because we've already defined e to the x there, right? Do it 3 times, and we know no matter how times we do this, it's going to be e to the x. So now let's evaluate all of these derivatives for 0. Well, it's going to be e to the 0 equals 1, e to the 0 equals 1, and I don't even think I need to do this, just all going to be 1, right? We know that this value every time is going to be 1. So this part is already done. We've already, in just a couple of steps, already figured out this part of the series. So we can already write so far. We have this, and all we need now is this and this, right? But we actually don't even have to write that. That's just assumed to be part of the expression, right? Because that just accounts for the natural scaling factor of the series. It's meant to represent how you can account for the original coefficient and recover it when you're interested at the derivative value at 0, right? So this is already done. All we need is this. This is literally all we have left to do. We just have to ask ourselves, what's the center? Well, actually, we don't even need to ask ourselves that because we know it's a MacLaurin series, which means that the center is just equal to 0. Or rather, we should say that x minus a equals 0. So we can say that x equals a. So if x minus 0, then we know it's just x, and just x is just x to the n. And so literally just by asking for each part of this coefficient sequence, we solved the series. We know that this is actually correct. We know that this, rather I should say I'm already aware that this is actually the correct series. If we look here, this should be what they get too. Yeah, they get this 1 plus x over 1 factorial plus x to the square over 2 factorial plus 3, right? So this is the best series approximation we can use for e to the x. And then, if we want to test it for radius and interval convergence, right here, probably ratio test is the best. So you do a to the n plus 1 over a to the n. I'm just going to quickly write it out. Give a whole bunch of steps. You should already be pretty familiar with this. If not, you probably want to go back and review some stuff. But this gets wiped out, this gets wiped out, this gets wiped out, this gets wiped out. So you're just left with x over n plus 1, right? And we're going to want to take the limit of this as n approaches infinity. We know that we can factor this out of the limit since it's treated as a constant. Any constant can be taken out of the infinity equation and just multiplied by it. So we get this as n goes to infinity, 1 over n plus 1. As n goes to infinity, the bottom is going to be infinity. 1 over infinity equals to 0. So we have the absolute value of x times 0. The only thing that can account for multiplying by 0 is infinity. So our radius is equal to infinity, and thus our interval of convergence is all real numbers, or negative infinity to positive infinity. And of course, we can't test these endpoints since it is infinity, so we would say that it is not convergent at those endpoints. It's gross without bounds. And that's really honestly as simple as it gets, and it's not really much more complicated than that. It's just sometimes you might have to do some algebraic manipulation to get into a form that's easy to analyze like that, right? Excuse me. So now let's look at a problem where the coefficient part, the f to the n evaluated at 0 over n factorial, isn't as simple, but I think this problem is still pretty easy. We just have to do a little bit extra work since, we're not dealing with either x, which is really easy to differentiate. So let's take 1 over 1 minus x. We know that this is going to result in this, or at least we should be familiar if we've done power series representations functions. This should not be a surprise to you, but the way we analyze it should be kind of new. All right, so again, we're going to do the same thing here. We're just going to try to get it to this form, right? That's all we're trying to do here. We're trying to use this form to analyze the series, or rather the function, and thus obtain the series that would best approximate it, right? Evaluated at 0 over n factorial x minus a to the n. So what do we want to do? Oh, we just want to differentiate it a few times and then kind of look at the behavior. So 1 over 1 minus x, I think the best way to do this is to just simplify it to this, minus 1 times negative 1. Remember, this is chain rule, so we're going to have to times it by, this cancels out, this cancels to a 1, so it's negative 1 times negative 1. That's going to give us 1 on the outside, 1 minus x to the negative 2. So that's the first derivative, equals first derivative. All right, so the second derivative, we'll just keep it like this. Negative 2 minus 1 times negative 2. And then again, chain rule, times negative 1. Negative 2 times negative 1 is just 2. So 2, 1 minus x, negative 3. That's equal to the second derivative. So let's do third derivative. Times 2. Again, we know this is just going to be negative 1 inside. So it should be, 6. 1 minus x to the negative 4. That's our third derivative. And then we'll do the fourth derivative, and that should be more, this is enough right here, but I'll just give you 4 just so you can really see. So it should be 6 times negative 4, and then times negative 1. That's going to be 24 on the outside. 1 minus x, negative 4 minus 1, negative 5. And this is equal to our fourth, or again, this is why we use this notation, our fourth derivative. And now let's just evaluate all these for 0. So first derivative was 1 minus x to the negative 2. This is just going to go, or rather to 1. 1 to the negative 2 is still 1, so it's 1. And then we have 2, 1 minus x to the negative third. Again, just going to be 2 times 1 equals 2. We have 6, so it's 6 times 1 equals 6. We got 24 times 1 equals 24, right? So we see that these are increasing, and now we just have to analyze what they're increasing by, and that'll tell us the coefficient expression, right? That'll tell us what this is equal to. So I think it'll be a little bit easier or more obvious if we just represent it a little bit differently. Or I mean, we could also do it like this, but I think I'll show both ways just so you can, it'll be a little bit more obvious, I think, if I just show it both ways. So let's analyze the first one. All right, it was this. And then it goes to this. And then it goes to, what is it, 6, 1 minus x to the fourth, and then it goes to 24, 1 minus x to the fifth, right? Well, what do we know about this? These should look pretty familiar at this point, right? We should see that this is just representing different factorials, right? This is just representing 1 factorial or 0 factorial. This is 2 factorial. This is 3 factorial. This is 4 factorial, right? Because you kind of notice that off the bat. So these here are just n factorial, right? Because this grows with n, essentially. So near the top is n factorial. Also just make it a bit more obvious doing like this, right? And then what's the bottom? Well, the bottom is kind of already done for us. We just have to write it a little bit better because we can't write a constant, right? We have to write in terms of n. So if we know that when we take a negative number and we subtract 1, that makes it not grow per se, but it increases the negativity of it, we could say. This is a fancy word for really not saying much, except we're just making it smaller. So if we want to make something smaller, we subtract. If we want to make something bigger, we add. So instead of, n minus 1, we would write n plus 1. That's really as difficult as it gets for the bottom. And then again, we want to write this all in terms of n. So it's n factorial over 1 minus x, n plus 1. And then shorthand version would just be, again, we don't technically even need this denominator. It doesn't really do a whole lot. It's literally just 1. I'm just writing it in a more precise way, right? So if we look here, we can literally just see that this is just n factorial. And then we can just add our 1. And then if we wanted to, we could re-express it like this, but I mean, this is literally fine too. But that's the more precise way to put it. So now we go over here and we're sticking this in again. Remember, we're sticking this into this here. So we have c to the n factorial over n factorial, x minus a to the n. And then you can see this cancels out. This leaves us with a 1, which we don't even need to write. So you have x minus a over n. And then was this a MacLaurin series? Nope. But I mean, if we look at this, we can see the original function 1 over 1 minus x. There's no shifting here. A is just equal to 0. Or equal to x, you could say. So c to the n, x minus 0 to the n, or c sub n is x n, which we write more precisely or even more compactly as summation, or rather the geometric series, excuse me, x to the n. And then of course now we can do our convergence and radius test. For this we can just apply geometric series logic to it. Absolute value r less than 1. We saw this inequality after plugging x in. Absolute value x less than 1. It's the negative 1. Our radius is 1. Our center is 0. So the interval convergence is going to be negative 1 to 1. And then we plug these in to do the endpoint tests. Negative 1 to the n. well, this is an alternating series. This is how the series is gonna go, or rather the sequence of series terms is gonna go. It's gonna be -1, and then -1 squared plus -1 cubed. That's gonna be -1, +1, -1, +1, -1. And it's gonna alternate like that forever, since the series, or rather the sequence of the terms as the limit goes from n to infinity is going to oscillate forever. We would say that this diverges, doesn't settle on 0, or approaches 0. So by the convergence test, we can say that it fails and diverges. And then for x to the n, when x equals 1, 1 to the n, this also doesn't converge to 0, right? The limit of the sequence of the terms does not converge to 0 as n goes to infinity, right? Because we would just be summing 1 forever. And the partial sums, of course, would be 1, +2, +3, +4, +5, +6, right? And that increases without bound to infinity. And so slightly different reasons, but they both diverge. So we cannot say that the endpoints converge, and thus we would have to write in this notation. We would not use brackets, use parentheses. And that's really, I mean, the problems get a lot more complicated than that, but that's the approach you can use for every single one and the angle of attack you want to use. And that's how you want to think about the Taylor series itself. Really, at the end of the day, just this, right? You do this enough times, analyze each point, understand what each one of these means, and I mean, that's it, man. You get it. So I hope this helped. Yeah, good luck on your tests, quizzes, exams, whatever. Peace.